Okay, let's look at some synthesis problems from the workbook. So this is on page 92. Let's see how many of these I can work on. These look kind of long, so I don't know if I'll be able to get through that many of them. Let's see, they look like they probably all use the same strategy. The first problem, it's giving us 3 carbon fragment, and it's asking us to take that to whatever this thing is over here. So I'm going to use the same strategy I've taught in other videos, which is to look at things retrosynthetically to kind of get back to the carbon fragments I need, and use some, forward thinking once I get to that point to do all the functional group transformations. It doesn't always work out perfectly. But yeah, step 1 is going to be, let's just look at the carbon-carbon bond forming reactions. And then step 2 is going to be kind of functional group transformations. Yeah. I'm trying to remember exactly how I broke it down in the other video. It was something like that. Okay, so I think the best one place to start is just numbering things. 3, 4, 5, 6. And so what we see here is that we have, on the left hand, our starting material is 3 carbons. And on the right-hand side, what we're trying to get to, we have something that's 6 carbons long. And this is a pretty good indication that all we have to do is figure out a way to join these 2 molecules together. And because this is organic chemistry 1, the only carbon-carbon bond forming reaction that we know is using that alkyne reaction with an alkyl halide, or acidylium ion reaction with an alkyl halide. And so we know we're going to be using that at some point in this problem. So let's take a look. Yeah, let's look at the big molecule. So probably what we're going to see, what I'm expecting, I haven't worked these problems yet, but we're going to be joining 1 carbon fragment from its 3rd carbon, so to whatever the other carbon fragment is, 4, 5, 6. So we're going to be forming a bond between 3, 4 there. So you can kind of think about it as somehow one of these molecules that's 3 carbons and another molecule that's 3 carbons must come together here to form this molecule. And we could try and go in the forward direction, but I think it's more useful or more helpful to think backwards. Okay. So yeah, what do we know if we're going to break it at carbon 3 and 4? We know that one side of that has to be an alkyne, and one side of that has to be an alkyl halide. And so all we're doing here is just trying to walk back. We're going to try and walk back. So I guess the first step really is to go through functional group transformations until we get an alkyne in the molecule that at least buttresses up against the part of the molecule that we know we're going to have to break it at. And so the thing that stands out to me here is that alkene. And so I think the first thing I'm going to do here is I'm going to get rid of that halogen. So we know that we can make the halogen from we could do a Lilic halogenation on this to get that halogen there. I'm kind of wanting for a solutions manual right now myself. Maybe we don't go that route. Let's see. Let's consider. Let's just go back to the alkyne first and see. I'm not sure what to do with that halogen at the end of the molecule. That's kind of making me concerned. Okay, let me make sure I haven't lost any carbons here. Good. So we're good in that regard. So yeah, so I know I can go from an alkyne to that alkene. That's a transalkene, so I can use sodium metal to get to do a reduction to get the transalkene. So that reaction I know. I'm not totally sure about this halogen thing on the end of the alkyne, though. That's kind of weirding me out. Okay, but yeah, so from there what we could do is, yeah, see, this is going to be a problem. Yeah, it must be this. I think they must want you to do this. You can see the thought process for these things, I guess, isn't always super neat. So for predicting reaction mechanisms like an SN2 and stuff, those I can do extremely fast. These, sometimes it's not totally clear where to go. Okay, so yeah, so let's say we go back in time here. You can get to, you can take this position here and brominate it using allylic bromination. You would get some other side products out of that is my concern, but maybe you just kind of have to eat that on this problem because I can't think of another way to do it. But yeah, from there we could go to this. Okay, so 1, 2, 3, 4, 5, 6. So if I'm going in the other direction, I know I can do allylic bromination for that. And then 1, 2, 3, 4, 5, 6. So I know I haven't lost any carbons there. I know I can go from the alkyne backwards to the alkene through just doing a reduction and trying to choose conditions that give me the transalkene. Okay, so now I can break at carbon 3, 4. Oops. And so what I'll get is 1, 2, 3. I'll put an alkyl halide on one side, sort of cap it with that. And on the other side, we'll just keep it as the anion. Okay. And then, so now I've got my carbon fragments. Yeah, this must be the strategy they want you to use. But yeah, so now I've got my carbon fragments here. And I want to just make those. So now I end up in kind of familiar territory here. So I want to take an alkene. I kind of think of these as recipes. I want to take an alkene to an alkyl halide. And to, an alkyne. And so what's my recipe? Well, I know with an alkene, no matter what, the first step I always have to do is radical halogenation. So I use Br2 and light, and I get the bromide there. That, unfortunately, is not in the right spot, so I want to go through E2 elimination to get my alkene back, and then I'll use HBr and peroxides to put it at the less substituted position. Okay, so that takes care of this. I've now made that. Okay, not an issue. So a few steps to get there. Now we need to take and figure out how to make the alkyne. And so I think we can just start from this, because we know we're going to have to do that. Actually, I did this in the last video, where I did this kind of synthesis. We start from the alkene. So remember, to make an alkyne, what you want to do is get a dihalide into the molecule. And so we can use bromination here to get that, and then we can just do LDA in excess, and from that we will get the anion that we're looking for. And so now we've got like this new retro palette. Now we've got this made. And so now it's just a matter of joining those two guys together, which is kind of already done. Okay, so I'm going to take, we've at least looked at the strategy there. That's where we started, remember, was doing the retrosynthesis. We're going to take that anion that we just made, and we're just going to combine it with the alkyl halide. And this goes through what we now know is an SN2 reaction. And now hopefully it's clear why this only works with primary alkyl halides. It's a strong base. If you use it with a secondary, you end up getting E2 elimination. Oops. 1, 2, 3, 4, 5, 6. Okay. So yeah, so now we've got our carbon chain formed, and we want to do our functional group transformation. So these are the ones that I did retrosynthetically. If you were confused about what the conditions were to get, if you were a little bit confused about what conditions to use to go between those retrosynthetic arrows, I'll show you that real quick. Let me double check here. So I took this molecule and I just flipped it around so it looked more like what it looks like in the problem in the workbook, just so I had the things facing the right way. But where we formed the bond was right here. So 1, 2, 3, 4, 5, 6. And then I've just kind of flipped it around. So I'll take this and I'll reduce it to the trans. Isomer. How do we do that? We take sodium metal and liquid ammonia. That's our reduction. And then the last step, which I don't really like, but I don't think there's any way around it, is you want to do allylic bromination here. So we'd use NBS for this. What you would really end up with is this, which is what we want, but you would end up with a lot of side product. Of that. And I'm trying to think if there's another way to put that bromine there. That isn't really extreme. Maybe we can do something. Let's see. Yeah, I mean, I can come up with other strategies. They start to get a little wild. So if you want to avoid this, so this is a lot of side product. And you would expect this to be the side product, or what I'm calling the side product. That would probably be the bigger product because this is primary and this is secondary. So you're going to get more of the secondary substitution than you will the primary. So this is not the cleanest synthetic route, but I think it's the only one I can see that's like kind of reasonable. If you wanted to brominate it and try and be more selective about it, you could try some other strategy like I keep trying to rack my brain if there's something I'm missing here, but I don't think there is. You could try some other strategy like no, I don't have anything else. I think this is the best you can do, unfortunately. If you've got a better synthesis, send it in, and I'll take a look at it. But I think this, unfortunately, is the best we can do with this. So yeah, so we end up getting a bunch of side product here. And I would say typically on an exam or something, we don't, we try to gear things to where you get only like the major product. You don't want to end up where your product that you're trying to get is like a side, is not the major product of the reaction, or you're going to end up with like a whole bunch of stuff you don't want. And that's kind of what you get here. But sometimes it's the best you can do. You kind of, as an organic chemist, just like in the real world, you're stuck with the tools you have. And in this case, our tools kind of don't give us an amazingly high yielding synthesis. All the workbook products seem to use a similar strategy. I keep thinking that I'm missing something here. Oh, it'll come to me if I did. Okay, and the next problem, it's asking you to convert propane into this thiol. Yeah, and maybe, you know, what it might be with the workbook is it might assume that you know chemistry that I haven't taught you yet. So we're kind of doing the best we can with the tools we have. So yeah, so the thing about this is, one of the nice things about this is, like, now we're kind of start to get a rhythm here, though. Because we'll say, okay, that's 1, 2, 3. This is 1, 2, 3, 4, 5, 6. Everything that we learned in our last problem can now be applied. The only thing that's new here is we've got this thiol group that we have to deal with. And so we have to figure out how to get that on there. And again, I think we might just be stuck with doing allylic bromination followed by a substitution reaction there. I'm going to rack my brain while I work this problem, and maybe I'll come up with something else. Okay. So again, you know, we're looking at, since we've already worked this problem, I'm not going to go through it, but, you know, we're going to break there. And if you want to do a retrosynthetic analysis to get going, we can do that. So if we go backwards, I would say, yeah, again, we're going to get rid of the thiol first. And we're just going to assume that that thiol started out, oops. We're going to assume that the thiol came from allylic bromination. And so we can go back from there. There we go. Yeah, so then we go back, we get rid of the bromine. And then from there, we want to make the alkyne. Okay, and then from there, we break it into its carbon fragments again. And that'll be an alkyl halide. And so, yeah, so now we see that, again, you know, it's the same problem that we saw before, where we need to make an alkyl halide, and we need to make this deprotonated alkyne. And so this part of the problem is, you know, literally identical to the preceding problem. We make those carbon fragments in exactly the same way. And this is something that you really see come up a lot, is once you sort of have a strategy down, you start to realize that, like, that strategy has to get implemented over and over again. You don't have to keep reinventing the wheel. So let's draw the top part, but going in the forward direction. So assume that we've made these using the strategy that we used in the last problem. So we connect those guys together. And that brings us to here. So that's here. Okay. And then it's the same thing that we saw in the last problem. So we're going to use sodium. We're going to use liquid ammonia. That's going to give me the trans alkene. So now I am here, transalkene, and then I want to use allylic bromination, which, you know, as I stated in the last video, I mean, the last problem, I'm not super thrilled with that as a strategy, but it's the best one I can come up with. So now we're here. Oops. So now we're in this molecule. And now, so the only real new thing here is you'll notice that in the product I have a thiol there. We don't have any direct way to, you know, make the allylic thiol, but we can do SN2 chemistry there. So if I just take this and take sodium SH minus, or sodium thiolate, then I will get, this is doing some, you don't have to write this when you're doing the synthesis, but this is doing some SN2 chemistry, and then I just get this as my product. Right? So again, not the most satisfying reaction just because, or a series of reactions just because this product you take a bad hit on because you have this big side reaction that happens where you end up with a lot of allylic bromination, but on the wrong side of the double bond. And there are ways around that if we knew more chemistry, but this is just kind of where we are, so it's not much we can do about it. Actually, let's see. I might be able to find a way. I cannot imagine this is the expectation, but let's say if we wanted to really get around that, what could we do? No. I think we're kind of stuck with that. I keep trying to come up with a better way. The problem is that you can't put anything that's a good leaving group or anything that's acidic onto that carbon fragment before you join it. So what I'm saying is I couldn't make, I'll walk you through my rationale as far as why that's the best we can do. So your two options really here are, let's take a look, let me find the product here. Yeah, your two options here are actually, let's just go back. We'll go back to the first problem because it's a little bit simpler. But your two potential ways you could work this problem are, one is you could take and imagine a way to put in the bromine after you join the two carbon fragments, right? And that's what we've been doing. The other way you could imagine doing it is putting it in before you join the two carbon fragments. So is there a way, this is what you should be thinking about if you're trying to one-up me, which I would be thrilled if somebody figures out a better way to do this. But how can I have this bromine already in the molecule before I join the fragment? So that, the obvious place you might want it would be right here. And we could figure out a way to maybe make that fragment. But even if you're successful in making that fragment, you don't end up getting this as your product. That's not what you get out of this. And the reason for that is that this molecule, even if you can make this molecule, well, let's say, so you'd start with the alkyne. And then when I deprotonate it with LDA, my problem is that I have this side of the molecule, which is nucleophilic, okay, or a strong base. But then right here, this part is electrophilic. And so I can get the molecule will start reacting with itself. Okay, so what we would see is, because you remember there's lots of these molecules in a flask. As soon as I deprotonate the first alkyne, I can get some sort of reaction like this to happen. And that'll just keep happening inside of the flask. So I can't have, I guess one thing you can take away from this is I can't have one part of the molecule that's nucleophilic or extremely nucleophilic and another part of the molecule that's extremely electrophilic with a good leaving group on it in the same molecule, because the molecule will then just react with itself. It's like trying to have a strong acid and a strong base present at the same time. They're just not compatible, and so you can't do that, right? So those reactions can't happen. So because of this problem, I don't think there's a way to add in the halogen before. I'm still trying to think of other ways before you attach them. Yeah. But, maybe there's a way to do it and I'm missing it, so it might just be a hard problem. So if you come up with that way, send it over, and I will be impressed. Okay, so yeah, so then we see the next problem, and we see, again, this is the same thing. What's going to be different in this one? Oh, actually, this one's a little bit more interesting. So here we have 1, 2, 3. Here we have 1, 2, 3, 4, 5, 6. But then we note over here we have 7, 8, 9. And so there's a little bit of an extra step here. So now we're going to do the same retrosynthesis. We're basically going to make we're going to make this just like we did in the last problem. But now we can see that we need this as our nucleophile. Hopefully we can see that. So let me draw out the series of forward reactants that'll get you there, so that if you're like super confused, you can cobble things together from that. So we want to use the same strategy. I'm not going to redraw this all out. We want to use the same strategy that we used to make this in the first problem. And we want to use the same strategy that we used to make the alkyne in the first problem. That part hasn't changed at all. Then we want to join these guys together. Okay, then we take that and we reduce it the same way we've been reducing. And we subject that to allylic bromination. And then finally, in our last step, what we need is this. To complete things. So the only thing here is this is the same kind of strategy like we used when we were swapping out the bromine for the thiol. But remember that most of these problems, and this problem is no exception, if you're adding carbon atoms into the substrate, you have to make those molecules. So we can't just invent carbon atoms. We're now going to have to make this alkoxide. So this wraps back in some of the alcohol stuff that we learned. So how do we make this fragment? Okay. So now you can see it's a smaller synthesis problem. Is how do I make this for this final step? So this is the part that we're working on now. We just have this one last step that we want to add that in. All right, so how do we make an alcohol out of this? We have an alkane, so we're going to start out doing radical halogenation here. That bromine is not in a spot that we like, so we're going to make it into the alkene. And now we can go directly from the alkene to, so we want to use LDA or some big base or something to do that. And now we can just go directly from that to the alcohol using hydroboration oxidation. H3, let's see, sodium hydroxide and peroxides. And that more or less gives us what we need. And then remember, if we want to turn this into the sodium salt, all we have to do is add sodium metal. And voila, we've got what we wanted. So we've now effectively, did I pick up a carbon atom there? Or lose a carbon atom? I think I lost a carbon atom. 1, 2, 3. Yeah, there should be another carbon atom there, another carbon atom there. Everything is the same, I just lost a carbon atom. Ooh. I guess the only thing that I would say that's different is in this step, I think LDA probably would be fine, but this step, you have to try and gear it towards getting the less substituted alkene. So, you would want to use something like terbutoxide, or LDA would be fine as well. Because you want to get I think it's the Hoffman product instead of the Zaitsev product. But yeah, so this is if I want to make an alcohol or an alkoxide from an alkane, this would be a way to do that. So you're trying to, when you're doing these synthesis problems, you're trying to come up with little tiny recipes that you can ultimately combine so that you don't have to keep doing the same thing over and over again. So just like what I would recommend is just like when we make flashcards, you might look at, my work up here is a mess. Okay, there we have 3 carbons. Okay, now we're good. There we go. Okay. 1, 2, no, something's still wrong. There we're good. Still good there. I'm so sorry, guys. Okay, so I lost it in the last step. That's it. Okay, so it wasn't as much of a mess as I thought, but I made it a mess. All right, but it's right now, I think. Yeah. Okay, but yeah, just like when you're looking at things and you're saying, okay, like if you have a reaction where it's like this, when you're making your flashcards, you have something that's like alkane to alkyl halide. You could also make flashcards that say like that are like alkene to an alkyne. And that you might want to note that these are like multiple steps, but they're sort of like recipes that you can combine to do chemistry in the synthesis problem, so that you're not like trying to recreate this every single time. You're going to be making alkynes a lot because that's the only carbon-carbon bond forming reaction you know. And it's just like when you're, if you're cooking, if you're making like if you're making like a cake, let's say, right? A cake has, let's say you're making a wedding cake. A cake has a lot of different components. It has a filling. It has its actual like cake part. It has icing on the outside. And when you're considering how to make a wedding cake, you'll break it down into the 3 different parts. Like, okay, I've got the icing, that's one recipe. I've got the filling, that's a different recipe. I have the actual cake, that's its own recipe. And then ultimately, I want to put these things all together. And this is the same kind of idea. This is like the icing recipe here. And maybe this is, you could have a different one where it was like, how do I take this to making a, I don't know, let's say a primary, let's say an alkane to a primary alkyl halide, because remember, usually what you end up with is not a primary. So you might have the strategy for this as well. So that might be the icing, and this might be like the filling for the cake. And then ultimately you can put those things together into the actual cake, by combining these things here. So it's hard. I don't want to undermine the amount of work that goes into getting good at this stuff, but it's something you're familiar with, even if it feels really unfamiliar. At least the logical steps that are involved in synthesis you're familiar with. We're just writing down reactions that are basically like recipes for making different things, and you're combining lots of different recipes to kind of get what you ultimately want. Okay, let's see. Yeah, they've got another one here. It's a very similar problem. Let's look at one of these other ones. These are all very similar. This one seems very different. Oh, here we go. This one's kind of interesting. Okay, so the very last problem on page 94 has you starting with this compound. Okay, and now we're going to this compound, where they're asking, how do we do that? All right, so the things that stand out to me about this are that I have 1, 2, 3, 4 carbons in my starting material. And in my final product, I only have 3 carbons. Right? So a carbon-carbon bond has broken somewhere in this molecule. And so this gives you another advantage here because we only know one carbon-carbon bond breaking reaction, and that's ozonolysis, so we know we're going to be using that somewhere in here. The other advantage you have here is that you're starting with an alkane, so you know that your first step is going to be radical bromination, because that's always the first step when we have an alkane. We don't know any other reactions. We have no choice. And that's going to substitute at the tertiary hydrogen because, you know, that's where these go. They go to the most substituted carbon they can. Okay, so now I have this, and I want to push towards ozonolysis. So remember, ozonolysis, we use ozonolysis to go from an alkene to a ketone. So if you were writing this out in deck, you might say alkene to ketone. Sometimes it's an aldehyde if it's on the edge of the molecule. I'll just get rid of this. That's how I think about it. Might not be how you think about it. Ozonolysis takes you from an alkene to a ketone. But what this tells you, if you know that ozonolysis takes you from an alkene to a ketone, is that at some point in this molecule's life it was an alkene. And we have an alkyl halide here. So my instinct is to just make an alkene out of it. Oops. And I can do that. I just do E2 elimination. When I do E2, it gets rid of one of these, and it'll get rid of one of my hydrogen atoms. So you'll note that CH3 is now a CH2. And so I'm really close to my product here. I make my numbering a little bit more consistent between these guys. Let's call this 1, 2, 3, and we'll call this carbon 4. What we need to do is we want to fragment. We're kind of doing the reverse of what we do when we do carbon-carbon bond forming reactions. We want to fragment the molecule into 2 different carbon chains. And so for the last step, we're going to use ozone, and the second step, you work this up with methyl sulfide. And so you'll get, I guess, this and some sort of side product here that probably decomposes into carbon monoxide and hydrogen gas or something. It doesn't really matter. We're not interested in that. It's not our product. So this takes us to finally what we want, which is a ketone. Okay? So if you're breaking carbon-carbon bonds, you're almost definitely going to use ozonolysis to do it. Just like if you're forming carbon-carbon bonds, you're almost definitely going to use the alkylation of the acylium ion, whatever, the deprotonated alkyne. And so you can use those to your advantage, right? So if you have these little tricks memorized, you'll note that in this problem, the first step, as I've said, let me use a different color. The first step here, I don't even have to think anything. I'm not using any kind of big part of my brain here. I just know that it has to be this because it's the only thing I know how to make with an alkane. And then when I look at the product over here, that cues me into the fact that I'm doing ozonolysis, so I must have had an alkene. Okay? So I'm not really having to think really hard about that. The only thing that I really have to consider is going between here and here. But that's not really that hard because I know I need to make an alkene, and I know I have an alkyl halide, and I know that I can go directly between those two. So the more of these you work, kind of the more tricks you sort of build up, and the easier and faster, easier these problems become, and the faster you can work them. If you look on page 95, there are some write your own problems. And that's probably a good idea. I might do that in a different video. I'll come back because this one's starting to get pretty long.